Welcome everyone for coming to my seminar, and for everyone that joined through the phone, thanks a lot for being here. Today I want to talk about a work that I have been doing with my colleagues here at AOML at the University of Miami as well as Florida State University. And this work is part of a paper that we are currently under review that we submitted to Nature Climate Change. And we have the review back, which had been fairly positive, but we have some work to do in order to finalize this. And the title of the talk that I'm going to be presenting today is Attribution of North American Heat Waves and the Pivotal Role of Natural Variability versus Anthropogenic Climate Change. And hopefully by the end of this talk, I will convince you that first, the idea is that heat waves are becoming more common. But how common? And I will show you that it depends on the location you live. When does the climate change signal will emerge on top of the natural variability? Could we make projections of exactly when, or more so approximation of when does the climate change signal of heat waves will emerge on top of the internal climate variability? So the overall of this story is, the overall goal is to enhance our knowledge of the relative role of internal variability versus anthropogenic climate change, which from now on I'm going to say ACC, and on extreme weather events. The objective of this talk specifically look at extreme weather events of the form of heat waves. And here we want to identify the most common spatial distribution, spatial patterns of heat wave over the US. And we also want to quantify the time frame when the ACC signal will dominate the occurrence of heat waves in the 21st century. So what I'm calling here time of emergence. And we have a hypothesis for these studies. The hypothesis states that while internal variability currently dominates the occurrence of heat waves in the US, ACC will gradually assume greater importance as we progress into the 21st century. However, the relative influence of internal variability versus ACC is highly dependent on the region. Thus, attribution I turn it on and then it turns off. Yes. So more motivation. Well, heat wave usually occurs during the summer. Good. And are associated with persistent atmospheric high pressure patterns. Could you please mute the mic for you on the phone? Thank you. So these atmospheric patterns lead to weather stagnation and persistent weather for prolonged periods of time, which lead, these patterns associated with heat wave could lead to persistent drought as well. And this figure from Mill et al. In 2009 showed that the ratio of warm to cold extreme temperature events has been steadily increasing in the 20th century. And right now we are in a 2-to-1 ratio of warm to cold extreme events. And this picture on the top right shows the number of weather-related deaths in the U.S. And heat wave is the leading cause, topping tornadoes, hurricanes, and all these other extreme weather. And some examples of these extremes, for example, the 1980 Great Plains heat wave, which killed about 1,700 people. And other notorious examples are the European heat wave in 2003 and the Russian heat wave in 2010, which were attributed more than 50,000. Could you hear me now? So for the model simulations, I'm going to use 1,000-year pre-industrial simulation from the NCAR CESM model with a natural, with 1850 forcing, where it doesn't contain any, it keeps turning off. It's on and off. It's working. Okay. Thank you. So this 1,000-year pre-industrial simulation will give me the statistics of extreme heat waves in the absence of climate change. Also from the same model, I'm going to use a 20th century historical simulation and a 21st century projection using the representative carbon path 8.5, which is on the figure here you see is the most extreme, is the most pessimistic scenario. And that one has 30 ensemble members. So the ensemble mean from that model will give me the climate change signal plus the model error, whereas the ensemble spread will give me a pure natural variability from that model. Also, I'm going to use some of the CIMIT 5 model with the same configuration, 20th century historical and 21st century forcing from the same scenario, the most pessimistic scenario. And the difference there is that the ensemble mean will have the information from the external forcing, the climate change forcing, but also we'll have information from, we'll not have the model error. The ensemble spread, on the other hand, will have information from internal variability, but also the model error itself. So they're slightly different. And all model simulation and all ensemble members evolve differently because of difference in initial conditions, but they are subject to the same external forcing. And also all models, since they have a different spatial resolution, all models were interpolated to the same resolution as the 30-member ensemble from the large ensemble simulation, which is about 1 degree in the atmosphere. And this is a list of the model I'm using, just to show you. On green is the large ensemble. I have 30 members there. And on the yellow are the CIMIC models where heat waves are calculated from. Also from the green, I calculate the heat waves. So I have daily data and monthly mean data from those models. And the one in white, I only have monthly mean data just to assess general circulation. So how do we define heat waves? There's many different definitions of heat waves. One difficulty in defining this extreme event is that it's extreme, but it's large scale, and it's also very persistent in time. So you don't get many extreme events that kind of gather all these conditions. So you have to be very careful in your definition. For example, here I'm using just for the summer month, starting in the 1st of June to the 31st of August, I define a temperature anomaly, daily temperature anomaly. And from that temperature anomaly, I define a 95 percentile threshold. So any anomaly that's larger than that 95 percentile threshold is kept. Everything else is set to 0. From those anomalies that are kept, I apply a spatial smoothing, a sliding window smoothing in a spatial sense, because heat waves are large scale, and you want to filter out what's known as hot grid points. So a heat wave is not just one grid point that has an anomaly larger than 95 percentile. On condition 1 and 2, if that's met, then we apply the third condition, which is the temporal smoothing. So we remove any temperature anomalies that does not persist for more than for at least 3 days. So that's given by the fact that heat waves are also very persistent. So we want to remove the high variance synoptic type weather. So for each of these, we create many maps now. So these are time series and time series of maps, spatial distribution maps. We merge it into clusters. And we use what's known as the agglomerative hierarchical clustering algorithm, where you merge them by their spatial correlations. Initially, we have hundreds of heat stream maps. So we calculate the spatial correlation of those maps, and the one that has the highest correlation, meaning the ones that are the closest, we merge it into a single new cluster. And we keep doing that all the way until we have just one global cluster. But that's not of great use. We have to come up with a stopping criteria for this clustering, and we use what's known as the dissimilarity index, which is basically 1 minus the spatial correlation, intercluster spatial correlation. When that index is the maximum, that's when you have reached the optimum number of clusters. And for observational data over North America, we found that there are 8 optimal clusters. Some of the models produce 9, 7, but they're very close to each other, but you want the models to be as close as possible. This is how it looks like, working your way from down the window. These are the 6 clusters on the bottom, and then we keep merging them based on their spatial correlation. Of course, if you go back, we say that 8 is the optimum. But here I'm showing you just 6. That means that we're merging clusters that are independent from each other. So if you keep doing that, you end up with a global cluster, which is shown on top, which you could use for some studies, but it's not what we're doing here. So we say we have 8 optimum clusters, and those are shown here. On the left panel is the observed clusters, and on the right panel is the pre-industrial run from CSM1. And you see that the model reproduces very well these 8 optimal clusters with some exception in the bottom. So all the clusters, and I'm showing you in terms of temperature anomalies based on each of the clusters. So you see that the temperature anomalies are very large for these clusters, and these are only summer months. So imagine a 6 degrees anomaly for the summer months.
The model results are the 20th century?
This is from the pre-industrial, from the 1,000-year simulation.
Oh, I see.
Yes. And it's a but they are anomaly. They are defined by their own anomaly. So we linearly remove the model bias in the climatology. So, but those are too many clusters to present you today. So I'm just going to concentrate on a few of them. How I will decide which one? Well, I calculated the population that is affected by these clusters and found that these four, the western, the northern plain, southern plain, and Great Lake clusters. What is that? Is that Molly? Okay. So these clusters are the ones that affect the most population, and like you see, it ranges from 40 to almost 80 million people affected by them because of their large-scale nature. And the temperature increase over these regions are well marked for all of them. These are the summer temperature. Also, since I'm going to be looking at 21st century analysis, you want to make sure that the clusters are still there in the 21st century. So we perform the same analysis for the 21st century model simulation. On the left is the 20th century, the fourth cluster I mentioned, and on the right is the 21st century, and they look very similar. So the clusters are going to be there in the 21st century. The anomalies are about the same because they're based on a climatological temperature for the given century, just for easy comparison among the two, between the two. I look at the subseasonality of these clusters, and what is showing the red is the early summers, during early summers, and on the blue is during late summer. There appears to be very little seasonality when you compare a given cluster with whether it occurs more often in the early summers versus the late summers. And the error bars are given from uncertainty due to internal variability from just this CSM large ensemble simulation, whereas the whiskers, the larger outside bar, the whiskers, quantifies model errors as well from the CMIP. And you could tell that the southern plain clusters tend to occur more often than the others. So now let's get into the real results here. So we want to assess natural variability versus climate change, right? I calculated from the 21st century the distribution of signal to noise ratio. I define the signal as the ensemble mean of all the models. So that's the climate change signal. And the spread, the difference among each ensemble member is defined as here is taken as the noise. So you want to know how much signal to noise ratio there is. You see that for the top cluster, which is, I call it the Great Lake clusters, the signal to noise ratio is about 1.6 in the 21st century. And same for the western cluster is about 1.8. But for the Great Plain cluster, the signal to noise ratio is much lower. So this tells you that there is more uncertainty in future projection of heat wave over the Great Plains. And the question is why? The margin of errors here that I'm showing, the red is coming from the CMIP model, so it includes model error, whereas the blue is coming from a single model, multiple realization of the single model, the CSM large ensemble. So that's purely internal dynamics. So you could tell that most of the uncertainty is coming from internal dynamics and no model error by comparing these plus minus error bars. So why these are different? Why the Great Plain clusters are different? We have lots of ensemble members. We have several models, but we are attempting to tackle a problem that deals with stream data. And by definition, stream data is very rare, very sparse. And even if you have 100 ensembles, you're still tackling, you saw my definition of heat waves, it has lots of requirements that needs to be met. So we still need to come up with a way to assess to find out if our results are based on random error. So we use a Markov model, which is basically, it takes information from the temperature data over each cluster and come up with parameters for this Markov model. The E, G, and B parameters come from the statistics of temperature, surface temperature, which is defined here as X. we project this model into the future and come up with what's known as a stochastic generated Markov model. It has information of the mean, it has information on the variance, but more importantly, it has information on the shift in the distribution because of a skewness, so because of the third and fourth moment, because this model is forced by additive and multiplicative noise, as these terms here. So we integrate this model into the future. So we have defined a 92-day length of the summer, just to be consistent with our definition. We have 81 summers, so we repeat this 1,000 times. So basically, it's like having 1,000 models or 1,000 ensemble simulation. We do the same thing for the 20th century, from the statistics of the 20th century and the statistics of the 21st century for each of the clusters. You see that for the 20th century, on top, on blue, on the left column, for each of the clusters, they all look very similar. What is plotted there is 1,000 time series, one on top of each other. And it's very apparent that there is a negative skewness in that time series. So cold events tend to occur more than warm events. That's consistent with the surface temperature distribution during the 20th century. For the 21st century, the Western cluster and the Great Plains cluster switch skewness. So now there's more warm events than cold events. So it's very clear that there is a marked shift in the distribution of streams. But for the Great Plains, it appears that it's mostly broadening of the distribution, so enhanced variance or the fourth moment, the kurtosis, and not so much of changes in the skewness. And that becomes apparent here when I plot the PDF, the stochastic generated skew PDF associated with this Markov model. And what is shown here is that for the observed is in black, plus minus the margin of error. And in blue is the 20th century for the model, the CSM model. And in red is the 21st century for each of the clusters. The green shading is where the difference between the red and the blue are significant. So it's mostly for the Great Plains and the Western clusters that the PDF actually changed shape. And that could have some repercussion on when does the climate change signal will emerge. And this table is very complicated. I don't expect you to go over it, but basically what I'm showing is for each cluster, their population and the mean temperature increase over this region is about 4 degrees, which is consistent with the RCP 8.5 scenario. And I'm showing you the return period for a very, very extreme case, a 3 sigma case. So the return period on the 20th century is on the order of 400 years, independent of the clusters. Whereas for the 21st century, the return period of this very extreme temperature occurs every 17 years. Here, I'm showing you the return periods for the 20th century PDF plus just a shift in the mean, not changing the PDF, not changing in the higher moments. And you see there's about 50 to 60 years return period. And here I'm highlighting the importance of higher moments. I calculate this return period just based on the shape of the PDF of the 21st century PDF without accounting changes in the mean. And you see that changes in the mean are important, but also changes in the shape of the PDF are very important. So the nonlinear process are also very important, which are often not taken into account in these climate change studies. Also, I want to show you that the ratio of warm to cold streams during the 20th century, like I said before, is from 0.6 to 0.7, whereas for the 21st century, it's expected to be, depend on the region, it's about 1.7 for the Great Plains, but it can go up to 10 times more often to have a warm stream over the Western region, which highlights the fact that the PDF is actually shifted from a negative to a more positive skewness. So how does that lead to time of emergence? Here I'm quantifying the distribution of the tails of the temperature distribution. So it's basically the distribution of the distribution. So I'm looking at just the stream cases. And I'm going to use what's known as in the stream value theory community as the generalized Pareto distribution with shape parameters, scale parameters, and threshold parameters. And here I'm going to calculate the PDF for 20th century and 21st century for each of the clusters. And you see that they're very different for the Great Lakes, again, and the Western region, and not so much different for the Great Plains regions. And that will have some repercussion of when we're going to see the time of emergence. And from this PDF, I'm going to get some parameters to calculate when exactly we might expect climate change signal to influence heat waves. And that's what's shown here. This is a very complicated plot. It looks very simple, but there's a lot of information there. So I calculate what's known as the probability of necessary causation, so PN. It's basically trying to tackle the problem of if we have climate change, what's the likelihood of having heat waves, for example? And or in another sense, let's say a heat wave occurred today, and what is the probability that it was due to climate change? So we get this p-value, this p0 value from a word that doesn't include climate change, so our pre-industrial simulation. And the p1 value comes from the factual word, which includes climate change. So we're going to use the 21st century here. Here, I'm going to look at a stream that are greater than 3 standard deviations, temperature streams that are greater than 3 standard deviation over the heat wave regions. And the map, the figure there is basically a time series. On the x-axis, you have from 2015 to 2095. And what is showing here is the probability of a heat wave being caused by climate change. I bin the data, for simplicity, I have just 3 bins when PN is less than 0.1, meaning that climate change is not the main cause, for example. It's not as important. I have on red that PN greater than 0.5, meaning that over half of the heat waves are due to climate change, or at least climate change is a necessary condition for that heat wave to have occurred. And from simple eye inspection, you see that there are marked difference depending on where the heat wave occurs. For example, for the northern plain, we may not expect climate change signal to emerge all the way up to 2056 by just reading this dashed line here about 0.5 when it intersects the boundary between the blue and the green shading. So that doesn't occur until 2056. In comparison, for the Western region, it's much earlier. It does occur much earlier for 2028. So you might expect climate change to be a major part of heat wave over the Western region. And also you can see if you're going to merge this 4-panel plot into 2-panel plots, you could lump the heat wave over the Great Plains into one group and the other 2 into another group. So the early emergence and the late emergence. So why there are differences in time of emergence due to ACC? There are large uncertainties in heat wave projection over the Great Plains. As you see, the PDF broadens, not only changes in the skewness. So that could lead to uncertainties. Also, but that's kind of, it's not a very, to me, it's not a very nice problem to tackle. I want to tackle more of a geophysical problem and not a statistical problem. So I want to look at potential physical mechanisms that could describe this difference in heat wave projections. So one mechanism involves changes in atmospheric circulation by what is known as the Arctic amplification because of asymmetric global warming. So you have, instead of having a jet stream that's more zonal, you have more wave-like activity, which could lead to more atmospheric blocking and extreme events. The second mechanism is a more local mechanism. It's known as the land-atmosphere feedback, where involve changes in soil moisture and how it communicates to surface temperature. That's very local, and is present in the Great Plains, but it's not present in the other 2 regions. So to look into the general circulation, or the How does it look like during these heat waves? I composite all the heat wave event and look at the mid-level circulation, which is plotted by the string function in black, and the precipitation anomalies. You see that for the Great Plains regions, the precipitation anomalies are very large, negative anomalies, and kind of like over on top of right below the circulation anomalies. So that hints at the importance of the land atmosphere feedback in those regions, where it's not so obvious in the other two clusters. So in this figure, I will explain step by step how does the potential mechanism might play out. So in the top label A, on the top left, what I'm showing you here is basically the correlation between atmospheric storminess, transient eddies, and surface air temperature. So you see that it's dominated by the negative correlation over the jet regions. And basically, if you have more storminess, and this is all summer months, if you have more storminess, you have cooler surface temperatures. The panel label B, right next to the other, is the future trend in the storminess. Same transient eddy, looking at the trend of 21st century minus 20th century, and it looks very similar to the correlation that I show you on panel A. So the storminess in those regions are mostly expected to decrease because of the Arctic amplification that I mentioned earlier. So you could argue that surface air temperature based on the trends are expected to increase because of their negative correlation to the storminess, which are expected to decrease. But that doesn't explain anything about the Great Plains. If you see the panel A and B, there's nothing over the Great Plains. That's where panel C comes from. Panel C is just the climatology, 925 millibars, low-level wind for the summer months. And in color, it's just the meridional component. So you see there's a very strong south to north wind coming from the Gulf of Mexico into the Great Plains. This is known as the Great Plains low-level jet, which brings most of the moisture and moisture convergence and lead to precipitation on the summer months for the Great Plains. On panel D is the composite of when we have a heat wave over the Great Plains. How does the circulation look like? Well, it kind of weakens the low-level jet because of the presence of the anticyclone there over the Great Plains. So it's kind of like weakening the climatological jet when we have a heat waves event. So it kind of like depletes moisture transport, which through the land atmosphere feedback exacerbate surface temperature.
Where is that decrease in
panel D, negative.
Over the Texas?
Yes. In panel E, what I'm showing you here is the trend in the low-level circulation, 21st century trend. And you see that it matches the climatological low-level jet in panel C. So basically, the low-level jet is expected to increase. What that tells you that under climate change scenario, we might expect more moisture transport coming from the Gulf into the Great Plains, which could actually slow down the effect of climate change on surface temperature, because this region is strongly coupled. Surface temperature and soil moisture are strongly coupled in this region. So an increase in the moisture transport will slow down or attenuate the effect of changes in the mean. That's great. The problem is panel F. Panel F is the variance, difference in variance, 21st century minus 20th century. And it appears that during the 21st century, there's going to be more variability in the low-level circulation. So variability introduces uncertainty. And that kind of explains the broadening of the distribution that I showed you earlier. So the enhancement of the mean low-level jet will attenuate the mean shift in the temperature. So it will attenuate and delay the time of emergence of climate change signal in terms of heat wave, but the enhanced variability will add to the uncertainty, which also will delay the time of emergence. So in conclusion, we have characterized the most common heat wave patterns over the US, which hasn't been previously done. basically what we have now is kind of like an EOF analysis of the streams. That's what the cluster analysis do. We showed the most dominant clusters and their spatial distribution. We also showed that the internal variability will dominate heat wave occurrence over the Great Plains, and the time of emergence of the climate change signal will not be up to all the way up to 2050 or 2070 in the most pessimistic climate change scenario. The ACC forcing, the climate change forcing, will dominate over the Western and the Great Lake regions, with much earlier time of emergence in the 2020s and 2030s respectively. And we also showed that the later time of emergence of climate change signal over the Great Plains is a result of the projected increase in the low-level jet, but it also is a result of enhanced variability and projection of the low-level jet, which will attenuate the climate change signal. And large uncertainties, like I say, is because of the enhanced variability of the low-level jet, projected variability. Whereas in the other two regions, over the Great Lakes and over the Western regions, these regions are now, the land atmosphere feedback is very weak. Over the Great Lake region is because of lack of radiation, whereas on the Western region is because of there's enough radiation, but there's not enough moisture, so the land atmosphere feedback is very weak. So in this region, the reduction in eddy activity, the storminess, and the strong negative correlation between surface temperature and this storminess over these regions increases the possibility of heat waves, which also brings earlier the time of emergence of climate change signals. So basically what it does is changes the shape of the PDF on top of changes in the mean PDF. Thank you.